Hi everyone, welcome to today's video. The topic of the video today is soil testing parameters and GTS NX verification. So the video will be divided into several sections, and firstly, we will explain why is the soil parameters input important for engineers. And with the part 1, we will discover about the soil parameters calculation, especially in the laboratory testing. We have the physical parameters, mechanical parameters, and how the soil parameters apply in the practical application. And with the part 2, we will explore the GTS NX soil constitutive models. So we will have various constitutive models in the GTS NX software, and we also have the nonlinear parameters need to be assigned, and how the soil test wizard in GTS NX will help engineers to validate their input from the soil parameters data, soil investigation data to the software. So, and with the part 3, we will have the finite element method model verification. So we will take example of the 3 tests. So in the laboratory test, and compare that result to our GTS NX simulation by the finite element method. So we will simulate 3 tests, including the UCA test, Oedometer test, and the Triaxial Test. Why is the soil parameter input important? So to answer this, so you can see this table is represented for the in situ soil investigation data. So we have different soil parameters, and then engineers need to input these parameters into the GTS NX. So as you can see, they need to transfer some of the parameters from the soil investigation data. So that will have some of the some of the errors, because the accuracies of the soil behavior estimation is completely depends on the engineer's input. So any misunderstanding between the actual soil data and the software parameters may lead to the errors in the inputting and causing the errors in the analysis. So now we will go to the part 1, soil parameters calculation. So to understand that the inputting, so we need to understand the soil parameters. And with the soil parameters, we will discover about the physical parameters, mechanical parameters, and how the practical application, like we use these parameters in a practical in the field. And physical parameters, you can see the soil will have the we will have like the solids and the voids, as you can see in here. So as idealization, so we will have the air, water, and solid, because in the voids we will have the air and the water phases, and from that we will, as in the situ soil, so we will have the sandy soil, clay soil, chalk soil, silty soil, peaty soil, and loamy soil. It is the different combination of the 3 phases here. And at the soil, we will have the about the physical characteristics. We will have the cohesion and the friction angles. So the sand soil is represents for the highest friction angle. So we do the physical test by the Grain-Sieve test, and as a separated with strongly in the cohesion values. So we will have the clay soil. In the clay soils, we will use the apparatus to investigates the physical characteristics of the clay soil, and you can have a clearly explanation from the soil mechanics fundamentals of the Professor Mooney in 2015 for references. So about the mechanical parameters, so we will have the uniform settlement, we will have the tilting or distortion, we will have non-uniform settlement. So that is the loading and the displacement behaviors of specific structures. So to find out the relationship between the loading and the settlement or the tilting behaviors, so we will mention about the mechanical soil parameters. So several tests was conducted, like the Oedometer test and the Triaxial Test and Triaxial Test, and the most accuracy is you testing the soil directly in the field, right? So that's why we have several field tests for discovers the mechanical parameters. So about the Oedometer test, so as you can see, we will have the placing a load, and then directly that load will press to the that load will become the load into the basement, and from that we will record the displacement and the vertical loading based on the times we have the loading, and we decrease the loading, so we have the loading unloading phases, and from that we will have the consolidation phases with the time, and the CS and CC value also could be determined, and the CV values, which is important to have the displacement with the time. So you can reference from the same book. And about the Triaxial test, so we will have the shearing plane between the upper part and the lower part. So from that, the shear strength will be found out from the shearing load. And you can see we have the shear stress and shear strength, but with the different soil, with the different density, of the relative density of the soil, with loose relative densities, we will have this curve, and with the denser one, we will existing a peak and like a decreasing to of the shear stress and the shear strength behavior. So talk about the clay. We talk about the sand materials. So we will mention about the latency. So the latency, as you can see here, is the shear stresses through the surface through the particles. So you can see each of the particles is represented by the circle, and when it's shearing, so it will have the transitions of the movement of the upper particles causing the shearing, and as you can see, it is upward from the movement will upward of the upward place on the lower soil particles. So that's why we will have the latency. This we call the latency. That is important for adding into the soil for the deformation, the shear strength. However, the difference is you find out the shear strength, shear strength of the soil with the specific failure plane. So that is not accuracy estimate the shear plane of the realistic soil. So that's why we need to discover another laboratory testing that is will be directly estimate the shear length of the soil. As you can see, here is the triaxial test. With this kind of test, so we will find out the shear length, that is the weakness location of the soil under the vertical loading and the horizontal loading relationship. So about the triaxial test, we can discover this test as a three-main tests can be determined. So with the undrained, we will consider about the drain and undrained, and consolidation and unconsolidation of the soil. So from that, with the triaxial test, we will have the unconsolidated undrained with the UU test, and CD test consolidated and drained, and CU test unconsolidated and undrained. So the bore pressure and the cell pressures are controlled to represent the realistic soil behavior, and from that the consolidation and the drain undrained behavior will be represented. So but in this test, because you control the vertical loading and the side loading by the pressures, so you can observe a realistic shearing plane and the shear strength of the soil, as you indicated in the result of the triaxial test, and that is very important for an accuracy for investigating performance of the soil, in the performance of the soil to inputting in the GTS NX software. So about the few tests data that we have. So we have a series of the tests are conducted to evaluate the soil properties directly in the field. So this is including the standard penetration test we call SPT test, and in this test we will use a loading as a hammer like 63.5 kilogram and drop it into the soil, and from that we can find out the loading, the displacement of the soil with the loading, and we also find out the Vane Shear Test, that is the VSD. So this test we will rotate as a moment to the road, and from that road at the bottom of the road we will have the shearing plane, shearing faces, and from that we will crossing like create the bending moment to the soil strength, and from that from the moment and the calibrations we can find out the shear strength, the undrained shear strength of the soil through the Vane Shear Test. Another also very popular and important in the field. So we have the cone penetration test, CPT test. So you can see like this one will use the cone tip stress and the sleeve frictions to find out the shear strength of the soil. So these data providing a realistic data for the geotechnical analysis and the like the final element method input. So about the practical application, actually we can have the different behavior based on the realistic construction. As you can see, here is the tank foundation. So in the tank foundation, you can see the loading of the tank will directly press into the soil, and it is just only the compression load. And so that's why in the practicals we use the triaxial compressions. So this is the directly mentioned about the compression loading. However, with the retaining wall, we will have the two different tests data need to investigate. That is the direct shear simple shear and the direct shear test. because it's called a shearing blend. When the soil failure and the pressing to the retaining wall. So we need to investigate the shearing blend, and that's why the direct shear test is applied in this case. However, the embankment, as you can see in this case, so the soil not only submerged to not only working in one case of the loading, not only compression, extension, but it's also including the shear strength, shearing. So also shearing. So as you can see, here is the compression of the vertical loading, and in here causing the shearing. But in here, in this position is actually behaved as an extension. So that's why we need to discover and we need to input in the software based on the practical consideration of the loading. So from that we can have the correctly the application and the value uses of the specific test from the laboratory testing or from the field testing for the specific construction. Now we will go to part 2, GTX NX soil constitutive model. So in this part we will discover 3 sections. Section 1, various constitutive model. Because in the real soil investigation data, so to inputting in the software, so in software we'll represent that kind of soil into a constitutive model. Typically will be molecular model and hardening soil model. So about the next section we will go through about the non-linear parameters, because the soil not only working in a linear condition, they working in a non-linear status. So to capture the more advanced in the non-linear status, so we will need to understand about the non-linear parameters. So and from that we can input into the software that needed for the non-linear parameters. And finally, we will discuss about the soil test wizard. In this tool, so GTX NX provide this tool for engineers to check and validate their inputting in the software, because this one will help you to generate a curve that is represented for the investigation data curve. So from that we can have a roughly compare and check before you start the further simulation. Okay, so now we will go to the section 1, various constitutive model. So in constitutive models, we have 2 general represent for the one is the linear consideration of the molecular models, which was very popular for engineers to do the simulation. However, if you, in case of the advanced simulation, so you can consider about the non-linear simulation, including, so this is the hardening soil, and especially so the small strain stiffness is considered simulation for the earthquake, seismic loading. So you can see here's the realistic behavior of the soil. However, we will use the tensions to represent the stiffness, and from the stiffness, so we can have the based on the linears of the hook law. So we can find out the strength. Yes, so this is the molecular model representation. With the hardening soil models, we can consider about the loading unloading behavior, and it also have the behavior of the non-linear of the hardening, increasing of the stress strain behavior, the stiffness dependent during the simulation. And another cases is the sand simulation, which represent for the another a very important case. This is the liquefaction. So in liquefaction, we can represent it by the 2 simulation model to represent the variation of the void ratio during the liquefaction status. So this is the modified UPC sand and PM and PM4 sand that represent for the liquefaction condition. So along with that, we also have some of the important soil parameters like the soft soil or the more modified complaint model and the others will represent for the condition that you want to simulate, like the clay soil. In rock soil, generalized, we will use the Hochbrodt model. So this is represent for the rock soil model that is quite popular in the simulation. In the constitutive models that we need to further discuss is about the real soil and the final element behavior. So you can see this line, this blue line is represented for the real soil behavior. However, in the software, it's very difficult to correctly represent it with the curve bending for each of the soil. So that's why we will generalize the relations, the curve based on the linear behavior, based on the secant stiffness. So from that, we can find out the stiffness, the Young modulus, to represent for the curve line. That is the linear behavior between the of the soil. And after the peak, we will represent by the line. This is the examples of the molecular models failure criteria. So in this slide is the linear elastic perfectly plastic representation for the in molecular models for the realistic soil behavior. So in this case, it's the differences between in the real soil. After the peak, they will have a decreasing, and with the increasing of the strength in this stage, there is no further stress increasing. But in the molecular models, in here we use the peak, and after that peak, there is no further strength considered of the stress in this case. So that's why non-linear models can consider about this stage, and this is the hardening soil model. So this is the figure to represent for the soil behavior and the molecular models. But in simulation, we want to understand the more realistic behavior. So that's why we need to further discuss about the hardening soil model, the importance of the stiffness that we need to consider. So this is an example of the soil retaining wall. This is of the excavation cases of study. As you can see, here's the result. But before that, when the engineer input the data, so they will input 5 of the important data to the software. This is E50 reference and EOED reference and EUR reference. So each of these will be indicated like E50 will represent E50 reference represents the variation of stiffness during shear deformation. EOED reference capture the stiffness under compression condition. EUR reference consider of stiffness during loading, unloading condition. So after inputting this and based on the equation of the including, so the software will calculate the E50, EOED, and EUR. So based on your reference value, corresponding reference value. So after that, they will process this equation and from the inside the computer, and then they will output the result. And here's one of the results of the excavation data. So, and why we need the shear deformation, the compression, and the unloading loading. So, for example, in this case, as we mentioned before, so we will have the shearing plane in this phase. So we call E50. So this is considered about the shear deformation. Not only that, when you see the deform of the retaining wall, it will causing the EOED, it means the compression. When this one deform at this shape, so you can see it will have a compression loading to the soil. So that is why we need to consider about the compression loading for the soil. But with the excavation case, so we will excavate the soil. So we will excavate the soil here, and it will be the unloading in the bottom soil. So it's causing the unloading and decrease the load on the bottom soil, so causing the heave up of the soil. That is the unloading load and loading and unloading condition. So we need to consider about the stiffness of that in the simulation also. So about the stiffness, we need to have the stress and strength behavior. So after discover about the stiffness, now we will have the discover about the strain in the constitutive model. So actually this parameters is also very important in each of the real construction consideration status. So with linear elastics, you can see the stress and strain have the linear behavior. So with the increasing the stress, the loading, so we will have the strain, we have the displacement, right? So, and another case is the elastic perfect plastics. This is the molecular model as representation, and the linear hardening soil condition model. So this figure is represent for the schematics of the shear strength in different of the ranges. So you can see we will have the secant shear modulus and the shear strength relationship, but we have the different strength of the model. So we have the very small strength and the engineering strength. So in engineering strength, we will work some of the construction from the range of 10 power minus 3 to 10 power minus 1. So this is the range where you can use the ultimate state is the molecular model, or you can share the mechanism is the Duncan chain model. That is engineering strength. And cover of that, you can consider about the hardening soil standard, right? So, but in the GTS NX, when we consider about the earthquake, consider about the small strain, so we will consider another different small strain is range from 10 power 7 minus 7 to 10 power minus 3. So this is the strain range for considering of the earthquake seismic. So this one, then you can turn on the hardening soils with more strength for simulating this strain ranges. About the soil test wizard. So here is the table of the inputting as we see in the discussion before. So this one, after we inputting this one, so to validate this with our investigation data curve. So to do that, we will use the soil test. This is a wizard, this tool in GTS NX that will help you to validate the inputting data, this inputting data with the investigation data. So here you can see this is the represent for the Triaxial Test, and you will see this is the strength and this is the stress. So this is the stress strain relationship, and we will have the each of the curve based on the loading. So we will have the different loading. So this is the hardening soil model assigned in the GTS NX, and use this soil test wizard, we can represent the Triaxial Test data into the software. And another test is the soil test wizard. So this is the Oedometer test. So this is the this figure is the stages of the assessment, loading assessment. So we will have 500 kilopascal, and then we increase the loading for finding the settlement, and after that we release the load to 300 kilopascal, and after that we increase again of the higher loading because it's already have the previous loading condition. So we need to have a high loading to increase the settlement. So we have the 800 kilopascal increase, and after that we decrease the 600 kilopascal. So you can see the increase of the loading and the decrease of the loading. After decrease the loading and increase the loading and decrease the loading in the second stage, it is not settlement and back to the first stage because of the loading, because of the nonlinear behavior of the loading and unloading condition. So this is represented for the Oedometer test, which is also help engineer to validate their inputting data for the soil test. So the last part of the video today is GTS NX Verification. So we will take three example laboratory testing and use the GTS NX to simulate that testing in the software. So and then give the comparison result. So the first test we'll discuss is about the Unconfined Compressive Strength, we call UCS test, and Oedometer test will be the next one, and the last one is the Triaxial Test. So in this first UCS test, this is the lab testing data. So we will have the specimen as represented in the figure, and then we will put in the machine to set up the loading, the displacement, and then we will have the and during the compressions, so we will have the loading, and in here we sort the bulging effects, which is the have the the bending in the two sides because of the compression loading. And this is the result of the testing. So you can see here is the vertical line, which was the compressing under the compression load after the bulging effects. So we will have the vertical line of the loading from the top to gradually propagate to the bottom. So that is the testing. So now we will have the GTS NX simulation. So to represent that condition, we have the UCS test with the specimen dimension is 5 centimeter in diameter and 10 centimeter height. So the ratio, this is the ratio, popular ratios of the H per D is equal to 2. So in this table, we represent the soil molecular soil parameters input. So with the parameters, we will use the drain because the specimen is don't have time much to have the undrained condition. So that's why for water go out, so we will have the consider of the drain. And Young modulus is we use 18,000 kilopascal to represent the peak of the soil of the block of the specimen we use. So Poisson ratio is 0.3, unit weight is 20, and unit weight of saturation is 20 also because we consider as the state of the already have the moistures in the soil. So and the cohesion is 25 kilopascal, and friction angle is 33 degree. So you can reference the GTS NX 5 at the UCS test final. This is the final of the running file for references, and in the model we will have the specimen, and in the specimen to apply the load, so we will have the creature's body at the top to control all the surface in this area, And at the bottom, we also use the creature's body at the bottom to fix this bottom. So we will fix the 2 points as the fix and the bottoms. But we apply the displacement as the prescribed displacement. But we use in GTX NX, we will have the total prescribed displacement and the incremental displacement. So in these studies, we will use the incrementals of the interval is 0.01 millimeters as a vertical increment. To represent the condition, and also applied the gravity to the specimen. So after solving that, as you can see, this is the loading for the poaching effects. You can see it's gradually increasing here as the observation of the laboratory testing. So you can see with the rotating and increasing of the loading as measured by the load cell. So we can see the bulging effect to the two sides and the displacement increasing, and the samples specimen is destroyed, and that is the UCS test in the laboratory testing. And we also see the bulging effect for the models, but in the simulation we cannot see the cracks because we use another model. But we still can obtain the bulging effects in the software. So this is the stress strain curve comparison. So you can see this is the stress and this is the axial strength increasement with the stress increasement. So with the laboratory testing based on the red color, so it's have increasing and decreasing after reaching the peak. But in the GTX NX simulation represent by the blue color. So it's a attention secondly from the 0 to reaching the peak secondly of the laboratory testing data and increasing at the line for the axial strength with the stress relationship. So there are 3 key highlights that we want to emphasize that. But before that, we can see this is the similar stiffness, right? So that is represented for the GTX NX constitutive models and the realistic soil. So 3 key highlights that we want to mention here is about the similar peak of the stress. As you can see, the peak in here is represented between the GTX NX simulation and the laboratory testing data. The peak is represented, and the stiffness evolution, you can see it totally similar stiffness as a secant stiffness for evolution between the laboratory testing data and GTX NX simulation. So from that we can conclude that the reality soil and constitutive models is represented for finding the stress and strain behavior between the testing data and the simulation. So now we will go to another test, that is the Oedometer test. We could be say that it as a 1D, one dimension consolidation. That is a consolidation term of simulation. And you can see this is the laboratory testing data. So we have the sample, we have the apparatus here, and we put the sample in the size inside in the middle, and we have a ball to transfer the loading vertically to the top of the specimen and have the plate to spread in the load equally on the surface of the specimen. And this is the final result. Based on the laboratory testing data, we have the final settlement is 11.15 millimeters. That is the result of the settlement during the loading phase and unloading phase. So you can see we have we consider two phases of the simulation. This is the increased loading phase. So the procedures will be 12 kilowatt, 25, 50, and 100 kilowatt gun. And then we decrease the loading phase as from 100, continue up from 100, but now we will decrease to 50 kilowatt gun, 25 kilowatt gun, and back to 12 kilowatt gun. So it's represented based on the color here, increasing and decreasing vertically and spreading to the surface of the specimen. So to represent that in the GTS NX software, so we will have the consider about the dimension. So this is the specimen. We have the 6 centimeter diameters and we have 2 centimeter height. So the D per H ratio is equal 3. So similar as the UCS test, we have the soil parameters, but now we need more parameters for the consolidation testing. So we have the UCS test with the units weight. We have the 17 and 18 for the dry and the saturation unit weight. So it means the wet unit weight, and we have the cohesion at 25, and we also have because this case is the loading unloading consideration, so we use the hardening soil model parameters for consideration. We use different soil and advance for consider of the loading unloading case, and we have the power of stress level dependency is 0.3. For the simulation to check the stress strain behavior, so 0.1 to 0.3 is selected, and we have three loading stage because we compress the soil and we decrease the loading. So we will have the OED reference is very important at 700, and EUR reference at 3 times of the OED. EOED is 2100. So the friction angle that we use is 25 degrees. Hydraulic conductivities as testing data we use from the testing data is 1.167 multiplied 10 power minus 8 meter per second. The Poisson ratio we use is 0.3. So you can have the reference GTS NX file names of the simulation as the Oedometer test final for your reference in simulation this testing. So we have the water level. As you can see, we will have the water level to consider about the consolidation, the specimen and water level for consolidation. And then after that, you will have the loading and the loading stages. So I also use the simulation here with the increasing of the construction stage. We use the construction stages. Firstly, we represent the stress, initial stress, and after that we increase the loading from 25, 12, 25, 100, 50, 100, and back to 50, 25, and 12. So we use that loading for the in the construction stage, and use the boundary condition that we accept the only settlement in the boundary condition. Only settlement is accepted, and the other like the movement from the left side and the right side will be constrained by the boundary condition. And at the bottom, all of the displacement even rotation will be constrained as a fix. So as you can see, here is the final simulation in the GTX NX software. So we have the result at the minus 11.04 millimeters. So that is the simulation result. So now we will go to the comparison between the simulation and the laboratory testing data. So here is the displacement that we read from the setup of the machine. The starting point is 5, and after that it's rotating due to the loading and unloading case. And we have the final settlement from the laboratory testing data is 11.15 millimeter. So about the displacement, you can see the displacement gradually increase from 0 to 2.688 e power minus 3 for the displacement. So here you can see the displacement increasing from the top of the loading. Yes, and this is the vertical displacement. And the simulation result showed that 11.04 millimeters was observed. And about the from the displacement and from the settlement of that result, so we calculate to the void ratio, because this is the very important data to for the Oedometer test, that we found out the pressure and the void ratio changes. So we have the E and P curve comparison. So you can see here we have the log pressure we use in the log scale, logarithm scale for the loading, and we have the void ratio for clearly represented of the loading and void ratio relationship. So with the loading increasing from 12 to 100 and decreased to 12, so this is represented by the laboratory testing and the GTX NX simulation. The result is quite much, and the final settlement is similar, as considered as a similar result and the behavior. So now we have the two key highlights that we withdraw from the comparison, that the simulation was captures similar void ratio and log pressures curve relationship, and it's also it means that it's already captured well by the hardening soil model to capture the variation in the loading unloading phase. So to highlight that the software can totally represent the nonlinear behavior in the loading and unloading condition of the testing. So in the last part, the last comparison result between in the simulation, we will discuss about the Triaxial Test. So here is the lab testing data. So you can see here is the tool for the shearing. So here is the loading, increasing the rotation. So it will have the loading in this area and press for the sliding, and have a restraint to, and from that it have the up. Here is the upper part, is the lower part from the shearing, from the reverse of the loading. It will call the shearing in here, the shearing plane, and constrained by the area of the frame. So here is the soil you can see, and here is the apparatus that like a frame to put your soil in this area. And here is the loading where you can have the compression load. So in here we use the normal force, that is we call normal force, and we use at 20 kilopascal, and we have the shear force, and the horizontal displacement will be recorded in the simulation. So, and you can see here is the result the result will cause slightly displacement and have relative displacement, and from that the shearing during that you have the shearing force and the displacement of the shearing blade. So you will have the shearing relationship between the stress strain of the shearing blade relationship. And here is the simulation. So in the simulation, we will use the 6 centimeter diameters based on the apparatus in the lab testing. So we will have the 6 centimeter diameters and 2 centimeter height. So the D per H is 3, ratio is 3. So the molecular models is used for consider in this case. We have the Young modulus is 5,000, and Poisson ratio is we use 0.35. Unit weight at the dry unit weight we have 18 kilonewton per meter cube, and unit weight set is 19 kilonewton per meter cube. So the cohesion is 5 kilopascal and friction angle just 10 degrees. So here is a very soft soil that we consider in the testing. So you can have the reference file. Here is the DS test file. So about the setting up of the model. So we divided into the 2 blocks. So the upper block and the lower block, we call the top block and the bottom block. So the constraint is different because the shearing strength, that is, so we consider about the we consider about the y direction. So as you can see in this figure, we shearing in the y direction. So the displacement in the y direction is accepted for the top block. However, the settlement also accepted, but the vertical, but the follow the x direction will be constrained. But at the bottom block, we want to have a fixed block to because we want to have a shearing plane here. So we want to fix this block and move this block as a prescribed displacement. So about the prescribed displacement, we also use the node at the peak, and we increase step by step, follow we have the increase each step of 0.001 millimeters, very small displacement, to consider about the strain to find out the shearing plane. So here is the displacement observation. As you can see, we have the top block and we have the bottom block. After shearing, you can see this is the bottom block and this is the top block. Here's the loading of the vertical. As we say, like the normal force is 20 kilopascal view on the top of the surface of the top block. And here is the shearing plane. We observe the displacement. So here is the full block displacement. As you can see, this is the observation of the displacement. So now we will go to the comparison. So with the displacement is 20 millimeter observed from the laboratory testing data, and we have the shear stress is 6 kilopascal, and you have the relative displacement as you can see. And now you can see the figure of the displacement in the testing. So it's gradually increasing, however also have the normal force and have the relative displacement. So, and from that, we also calculate the similar result. You can see it's also have a similar displacement of 20 millimeters at the peak, and then the shear stress is the 6 kilopascal for the shear stress maximum. The peak of the shear stress is 6 kilopascal and the displacement is 20 kilopascal. Here is the translating with the consider of the peak, but the maximum of the shearing, because we continuous shearing, so the peak is 6 kilopascal considered here. So in this simulation, we have the evolution of the shear stress is captured, and the behavior is agreed with the laboratory testing data. Yes, that is the end of the video. So we hope that our discussion today in these videos about the soil testing parameters and GTX NX verification can help you to understand why the inputting parameters is very important for engineers, and we hope that can provide for you some of the important information like the soil parameters calculation and how about the constitutive models in GTX NX software and in the finite element method in general. And finally, we hope that our verification can help you to have a look that the condition of the nonlinear and linear can be represented by the software, and especially in GTX NX powerful software. So thank you so much for your attention.